So dimension reduction, we already talked about how data points, how data or high-dimensional points. And the examples we saw, the web, for instance, D is in the billions, or many times it's at least in the thousands, so it's very high. Of course, we saw that geometry looks different and all that, but in any case, efficiency-wise, it'll be nice not to have to deal with such high dimensionality, right? So it would be nice if we can reduce the number of dimensions, but of course, without changing the problem. So in just reducing the number of dimensions, we shouldn't lose properties, right? So we'd like to do that. There are two main methods of dimension reduction. So one is random projection. So it's difficult to represent very high dimensions on the board, right? Random projection just means that I can show you two-dimensional points, right? There are points in two space that are your data points, and you project onto a line. Orthogonal projection. And so on, right? Now, if you project 2 to 1 dimension, there will be a lot of problems. For example, you will have potentially 2 points which are on top of each other. So their distance in the projection is 0, is much, much less than the distance upstairs. Okay. Now, because you're reducing dimension, you expect the distance to go down. We'll see how much by a certain factor, but I don't want it to become 0, or I don't want it to become really bad compared to that factor. So that's one issue. So we want random projections which are oblivious to data. In this case, it'll be, they won't care about data, it's just random. But we don't want to lose all properties. So preserve some properties. Okay. And the properties depend on the problem, but for a first cut distances. So you want at least not to lose track of what the distance between every pair of points is. So you don't want 2 points like that to fall on top of each other. Okay. So this lecture we will see in detail how to do this. I mean, it's just going to say actually that you pick a random projection, pick this line at random, and then things will behave nicely. We have to prove that. We'll prove that. Okay. But so I want to go over the sort of general idea first before we start proving. In general, what will happen with random projections is that you'll preserve lengths to factors which are 1 plus or minus epsilon, right? So the length in the projection will be within relative error epsilon of the length over on top. Now, unfortunately, as epsilon falls, the dimension you need to project to is going to grow. We'll see how much, but I'll just write this down. The projection dimension is order 1 over epsilon squared. So if you want low error, you need to project to a very large number of dimensions, right? So if you want really low error, the dimension you're projecting to is going to be so large that it's not that useful. Remember, we wanted it to be computationally useful, so that won't happen with random projections. So random projections are good because you don't have to process the data. You can quickly get it just as random, just a random generator. But they are not good enough if you want error which is less than little over 1. And you do want error less than little over 1 for a lot of problems. We'll see that, not today, but we'll see that in general. So random projections are used extensively in theory because of A. Now, I forgot to stress it, but with random projections, we'll prove that every pair of lengths is preserved. So with high probability, with no exception, every pair of lengths is preserved. There is a probability of failure that the lengths are not preserved. There is a small chance that a random line will put 2 points one on top of each other, right? As you can imagine, the chance is very low. Okay, but there is a chance. But what this is saying by every is that with 99.9% probability, we can make sure that with no exception, every pair of points is closed. Okay? Now, that's nice. In theory, we use it a lot, but there will be another set of projections. There are globally essentially two general methods of projecting to reduce dimension. One is random projection. The other one is principal component analysis, which also we'll see in coming lectures. That has different properties. Projection length behaves very well, much better than the epsilon error, okay, but only when averaged over data. So it's not true that every pair of points the distances are preserved. It is true that on average the distances are preserved very well. So some pairs may behave badly. Okay? Theoretical use is a little restricted because of this fact that it is not true for every pair. But it is used in stochastic mixture models, which likely at the end of this lecture you'll already see a mixture model, and we'll come back to them later, right? But PCA is very widely used. In fact, for certain problems like nearest neighbor search, which you will see, PCA is more commonly used in practice than random projections, and random projections are more commonly used in theory than PCA. Okay, so PCA is not today. It's random projections today. Okay, so most of the lecture will be on random projections, and then at the end of the lecture, I'll start on Gaussian mixture models, which will continue also when we do PCA. So, okay, good. So here's some motivation for the kind of problems we can solve with dimension reduction, in particular with random projection. So as somebody said, in fact, a huge bulk, I don't know what the percentage is, huge bulk of machine learning and practical computation is precisely this problem of nearest neighbor search. What is the problem? The problem is the following. You're first given a database of n points in RD. N is very large. D is also large, right? You're given these points. You're allowed to pre-process taking a lot of time, taking polynomial time in n and d. Okay? N cubed, n squared, any amount of time, right? You do the pre-processing, and then once you've done it, then queries come along. A query is also a point in RD, and ideally you want to find the nearest database point to the query point, but very quickly in sublinear time. Okay? The data is n points in D space, so its length is nd, so you want to do it in little of nd, often in polylog time. Okay. Let's sit back and think about this. How about if d equals 1? Suppose I gave you points on the real line, right? And then whenever a new point comes, I must very quickly find its nearest point. Do you know how to do that? I'm allowed to pre-process. What is the pre-processing one might do for points on the line or in one dimension? Sorry? Sort. Exactly, right? Once you sort the points, then by binary search, a new point in logarithmic time, you can tell the nearest point, right? And you should think a little bit. You can do this in fixed dimension. In 2 dimensions, for instance, you can also do this, right? I won't go over that. But so that's the kind of thing we are looking for. Sort or do something, takes n log n time, fine. And then at the end of it, in log n time, you're able to tell what is the nearest point. We can settle for approximate nearest in practice. So we'll see that projecting the database points into a random polylogarithmic dimensional space is a good solution. We'll see that. We have to show you that. At query time, what we do is we also project the query point down to that space and measure distances. So the data points were here. We've already done this projection. Getting these is pre-processing. And query point comes along. That's a query point. Then we project that and see its nearest point there in the projection. We don't bother otherwise. It's not quite that simple, but we can think of it that way conceptually. Okay. Okay. Another example, a completely different example where dimension reduction is useful, and I'm going to give you. There are lots of examples. I'm going to give you only 2. Linear regression. What's called the overdetermined case. That's the following. You have a matrix A. Ideally, you want to solve equations Ax equal to b. There may not be a solution, so you want to minimize. You want to find an x so that Ax minus b is minimized. Overdetermined means A looks like this, and x is small dimensional. You want it to be approximately equal to b. B is also taller than, right? So this is interesting in the case when really is much taller than it is wide. N is much larger than D. That's called overdetermined, underdetermined if it's the other way, right? So here is a thought. You take a random projection of both sides. You must hit both sides. So I can draw the picture better. You have a matrix P, which looks like this. Right? This dimension is n, that's n by d, right? This dimension is n. I call this, well, I call this k. Okay. So, and then you solve the projected problem. Now, it's a much nicer problem because this is only a k by d matrix. Now, I won't prove this to you, but to prove that a solution to this is a good solution to the top, you have to do two things, right? You have to prove that for every x here, okay, this thing is a correct representation with an error of the length of this. So length of ax minus b for every x is roughly equal to the length of PAX minus PB. That's non-trivial. Why is it non-trivial? Because how many x's? So you could try to do that by union bound. I say for every x, this length and this length are closed for 1x, right? With a certain probability. So there's a probability of failure for 1x. Okay. But you have how many x's? You have infinitely many x's. You don't know what x is going to be the solution, right? You have infinitely many x's. So it's difficult to just apply the union bound. Okay. Yet it can be done. Again, I'm not going to do this in detail, but random projections can be used to solve this. Okay. There are many other examples, and I'm going to show you at the end some clustering example, k-means clustering, how you can cluster in the projection, and that's enough to get an approximate solution up on top. And we'll discuss this later. Okay, so the order of business is now I'm going to present the random projection theorem and proof, and then we'll go back and discuss these applications. So so basically I want what's called a length preserving projection, so, or you can call it distance preserving. We'll see that they are the same really. So we want a random length preserving linear projection from big d-dimensional space to k-dimensional space. K is much smaller. Okay. We want, so it's linear, so I want a matrix P. It's a linear transformation. I want a matrix P so that for every vector V in D space, the probability that the length of PV is within relative array epsilon of the length of V, right? 1 plus or minus epsilon wants to be 1 minus delta or higher. So the probability of failure wants to be less than or equal to delta. Okay, a few observations before we prove the theorem. I put the quantifier for all outside the probability, right? So this says for every V, probability is this high, right? So let's understand that that's important. What if I place the quantifier inside? So what if instead I say that the probability for all V, is that a nice state? Let's see if that statement makes sense. Probability that for all V, PV 1 plus or minus epsilon V is greater than or equal to 1 minus delta. So would that be possible? That's a stronger statement, right? This statement is for one V at a time. The probability is failure is small, it says, for each V at a time. But for every one of them, but one at a time. This says for everyone simultaneously this is true. So is that possible that we can make the stronger statement? I didn't make it, but can we? Why? Okay, but any other answers? I mean, huh? Yeah, so we cannot do that. Because, see, basically we are sitting in d dimensions. These vectors are in d dimensions. There are d degrees of freedom. There's no way in general I can reduce the degrees of freedom and keep anything sensible, right? Because there are d vectors. So null space is in fact one way to see it. So if k is less than d, there's a non-zero v in the null space of v. Null space of p is k by d, right? In d space, there's always some vector that p makes 0. And then if you have that vector, you get a 0 here, you get a non-zero there, right? So one nice thing to remember is 0 is never within relative error of anything non-zero, right? Never, right? Any non-zero. So you can't do that. Okay. So I can't put the quantifier inside. I can only do it once for one vector at a time. The original projection that was used to prove this theorem, it's called the Johnson-Lindenstrauss theorem. They use the following. They projected to a random k-dimensional subspace. In terms of matrices, their P was, so they wanted to project to a random k-dimensional subspace. P had rows which are a basis, just like a linear algebra basis of that subspace, which means they were orthonormal. Vectors are orthonormal, as you recall, if the length is 1 and they are mutually orthogonal, right? So that was their P. Their paper was very long. It was 50 pages. The difficulty was, first, how do you pick such a matrix? There's dependence between the rows, right? I pick the first row. The second row cannot be independent necessarily. I must make sure the dot product is 0. I must make sure of strict orthogonality. And that turns out to involve a very complicated argument. Both for generation, it's complicated. But to prove length preserving, it's very complicated because of the dependence. Okay? So we won't do that. We are going to do something slightly different where the vectors are not orthogonal, but still the whole thing works. We pick k vectors. Remember, the k is the number of rows of P, this thing. Right? I'm going to pick k vectors u1 through uk. I'm going to make each of them spherical Gaussian mean 0 variance covariance matrix identity. Just one more time, let's recap this, what this notation means. We introduced that last time. I want to recap that. So the variance covariance matrix of a random vector u. So each of these uses a random vector. So if you have a random vector in D space, its variance covariance matrix is just ijth entry is a moment of inertia, right? Is the expectation of the ith component times the jth. Except we want to make sure the means are 0. They may not already be 0, so you just subtract out the means. Okay. Now, it equals identity means that different coordinates are not correlated, so independent coordinates just means that. Right? Everybody's familiar with this, right? So just to recap the rules. So the projection is going to be given by, so I want to project the vector x, right? Its projection is just a dot product with these vectors. Okay, that's what I'm going to do. If your projecting space had an orthonormal basis, I would just take the dot product with that. That would be exactly orthogonal projection, right? This is not, right? These u's are not necessarily orthogonal, so it's not an orthogonal projection. But it's going to be fine for us. So we still will get length preserving property. Okay? So it's very simple. I pick k Gaussian independent vectors and just take dot products with them. So I get here a vector with k components, right? Instead of d components. Okay. We'll prove that for each vector v, the length of f of v is not exactly 1 plus epsilon, 1 plus or minus epsilon times length of v. There's a root k factor. We'll think about why the root k factor. Before we do that, let me just ask you, let's figure out what the expected value of v dot u. V is a fixed vector, u is random, right? The expectation is with respect to u. What the expectation of v or v dot u1 squared is, or at least an upper bound. Okay. So any sort of thoughts about what the expectation of v dot u1 squared might be, what the dot product squared might be, or how we might compute it? So what do you think the random variable v dot u1 looks like? U is random, v is fixed, remember. But what does the random variable, just the dot product, look like? Sorry? Gaussian. Yeah, it is Gaussian, right? Because it's actually the sum of some Gaussians. It's a Gaussian. Sum of independent Gaussians, so it's a Gaussian. So that's what makes this very simple, the argument, compared to taking orthonormal vectors. So v dot u1 is just a sum of It's just dot product, right? So sum over all j of this. The u1j, the components of u are independent because it's normal zero identity, right? The components of u are independent. So this thing is a sum of, v is not random, v is a fixed quantity. So this is a sum of d independent Gaussians. And if you add up Gaussians, the means and variance just add up, provided they're independent, right? So variance, you have to be careful. So v dot u1 is distributed. So the variance of this component alone is vj squared, right? The variance of this is 1, the variance of that is vj squared. So the vj squareds add up to the length of v squared. So you get a normal, this real value random variable now, it's a real number, is normal 0 v squared distribution, right? So with high probability, this is less than cv. This is just a constant times, there's a number of standard deviations. So there's a normal random variable, it doesn't exceed more than c standard deviations. So this quantity is much smaller than if v and u were collinear. If they're collinear, you would get that much, but you get a factor of root d of. Okay. This, I claim, should be reminiscent of something we proved already, and that'll be nice to remember. So we proved such a thing for uniform random from a sphere in d dimensions. So this is Rd, the big space. If I pick, if I have a fixed vector v, and I pick a random u, we proved that u unit length in this case. My u here is not necessarily unit length, it's of length d, so there's some scaling, but here unit length, we saw that v dot u will be less than or equal to 1 over root d, c over root d. But that's equal to v times u over root d, because v and u are unit vectors in that case. Okay. So I want to write this down, which I should have written on the slides, but it's worth remembering. I want to write this down carefully. So if we have two vectors, v, u in Rd, which are independent, then the dot product is less than or equal to c over root d times the product of the lengths. Product of the lengths is collinear, right? Dot product is 1 over root d times that. This was our equator theorem for spheres. We here argued for Gaussians, which is easier, but it's true for many distributions. So this is, if you will, the equator theorem. Okay, dot product is roughly 1 over root d times what it would be for collinear. Okay, so that's true. Okay, now I'm ready to state the random projection theorem. I'm going to state two theorems, and then we'll prove that. The proof will not be very difficult, actually, not much longer than the statement of the theorem. So f is the same as we had. I take k Gaussian vectors and take dot products. There's an absolute constant c such that for epsilon not too big, epsilon between 0 and 1, we have the following thing. Again, the for all is outside. For every individual vector in Rd, every one, no exceptions, okay, you take the length of f of v, the k vector, minus root k times v. I forgot to answer the question why root k, but sorry, let me just do that before we go. So, sorry, excuse me. So this expectation is constant, right? We saw that. If v is length 1, this expectation is, sorry, this expectation of the square of this is 1, constant. Okay? It's the length of v squared, but if v is length 1, this is constant. But I'm adding up k components. So I'll get k for the length squared of f and root k for the square root. So that's why the root k comes up. Yes? Because I had k components. Okay. The probability that there is a relative error, so it's supposed to be that. The expectation is that, well, it's not quite the expectation. The expectation of the square is the square of that. That's all we proved. And the probability that the relative error is more than epsilon falls off as e to the minus, very importantly, k in the exponent epsilon squared. I'm going to abbreviate for the future this statement here as the length of f of v is within epsilon error, relative error of this, right? That just means that. I mean, it means, it means the opposite, excuse me. Sorry. This means the opposite of that. Okay. This means that it's within relative error, but this is saying it's not, so that's an error, right? Okay. Where the probability is taken over random draws of the vector u used to construct f. In other words, v is not involved in the probability, right? And then a second thing, which is in fact a little more useful, on the lines of this picture that the lengths are preserved, it says for every epsilon and any integer n and k greater than 3 over c squared log n. So very important that k only grows as log n. Okay. Then I take these n points. Then for every set of points, now the for all is inside the probability, right? I'm asserting that with high probability, all of them hold. All the lengths are preserved. Okay. Now, that actually, all the distances are also preserved. I think this is stated on the next slide. So this is the distance between Vi and Vj on the right-hand side. On the left-hand side is actually the distance between f of Vi and f of Vj, right? Which is the same as f of Vi minus Vj. F is linear. So we'll see that that's useful. So everybody see rough, we'll come and prove that. Why is this true based on that? That's actually simple, right? Sorry? Any thoughts on why? Theorem 2 follows rather easily from theorem 1, I claim, and we'll write down a proof, but let's take a minute to see if we can guess that. So what is theorem 1 saying? Theorem 1 saying is for one vector, the projection is more or less length preserving. What's theorem 2 saying? Sorry? Convex, no. Oh, there's one word I want to hear. Huh? So we want how many lengths to be preserved here? We want n squared lengths to be preserved, right? So what might we do to get all n squared to be preserved from knowing that 1 is preserved? Union, did somebody say union? Okay. Union bound, right? So there's a lot of dependency. It's not true that the projections, these things are not independent, of course, right? Because Vi, once you know some Vi and some other Vj, then this is dependent. They're all the projections. So it's just a union bound. So I have n squared things to be preserved, but luckily this thing is in the exponent. So if you work that out, once I put k equals some high quantity times log n, this becomes 1 over n cubed or something, probability of failure for 1 point, and there are n squared points. You just have to multiply 1 over n cubed times n squared. That's still small. Okay. So we will actually write down this proof. Okay, let's prove the first theorem, right? Again, the proof is going to be quite simple. Before I prove it, I think I have some remarks, including the ones that I just made. The claim is for every V. What if I just wanted the statement for most V? So let's think about that. So statement 1, suppose I wanted this to be true, not for every V, but for most V. Okay. It's a simpler statement, but is it useful? Okay. So maybe you can say if the data for nearest neighbor search was random, I could just have a weaker theorem that says it's true for most V. Okay? Let's see if that's true. So I wanted a nearest neighbor search. I assume that the data points, the data set I'm given is random, is not the worst case set. Can I then use a theorem that says for most V I'm length preserving? Okay? Actually, you cannot, even in case the data is random. Let's think about why that is. I always need that for every V it should be preserved. Okay. So if it is a random data set, right, what does that mean? That means that most of that data set behaves well. But there might be exceptions even in that data set. And our nearest neighbor search says, I give you a query point. You must find absolutely the nearest neighbor or close to the nearest. I'm not allowed to make errors. So if the nearest neighbor is an error point, is an error-prone point, I can get it completely wrong. Right? I'm not allowed to do that. So nearest neighbor search, in fact, this is true of any optimization problem. If I give you an optimization problem, even a random instance, I want the optimal solution or the approximate optimal solution. I don't want to say that you can fail with some probability and give me nonsense, right? You cannot do that. So even if the data were random, I would still need this for all V. So I cannot use the weakest statement. And the weakest statement is very simple to prove. Suppose I have a random V and I want to preserve lengths, what would I do? Something much simpler than this. So I have a random d-dimensional vector V. It's random. And I want a projection where the length sort of represents that length. Not preserve exactly, but maybe within a factor. What's a good, simple projection? Take the first component, right? If the vector was random, all components are roughly the same, so the first component should be 1 over root d. So that's not interesting, right? But that's not also useful. Okay, good. The advantage of linearity of f is the estimate distance between 2 points is some fixed factor, 1 over root k, times the distance between their projections, right? And that's because the projection of the difference is just the difference of the projection. It's linear. So I could have just projected the points and looked at the distance, right? You need linearity for that, otherwise it wouldn't be true. Okay. K being in the exponent of the theorem is crucial, so you get logs because k is in the exponent. There are many other random projections known now. Gaussian is the simplest and easiest to prove. But for example, the ui can be taken as plus minus 1 random vectors. Intuitively, when d is very large, that's like things behave like the normal, right? Central limit theorem. Behave like the normal. But for smaller d, also something is true, but that's more difficult to prove. Here, we don't do that. We'll only do it for Gaussian. So, but there are many distributions now that for which random projection theorem is known. Okay, now the proof. We want to prove that that's true with high probability. Scale both sides, we might as well assume that v is 1. So if I scale v, both sides scale by the same amount. So I have no... nice thing about relative error is that I'm allowed to scale both sides by any amount, right? Any factor. Not true for absolute error, but we wanted relative error so we can scale. Okay? And so we may assume without loss of generality v is length 1. Okay? Now I just, again, this is a repeat, something I did earlier. So the dot product is the sum of independent random variables, and therefore the means and variances add up. So we get that this has distribution n0, 1. Okay. Now, U1, these dot products then are independent Gaussians. Each is distributed spherically, right? This length of v squared is 1. So each dot product is normal 0, 1. They're independent. So this is a k-dimensional identity matrix. F of v is a k vector, right? So the k vector is distributed exactly like that. And we apply the Gaussian annulus theorem we proved last time. The Gaussian annulus theorem told us that if you pick points from independent Gaussians, k points in this case, the length will be about root k, because I picked k points, each of Gaussian normal 0, 1. Root k, the probability that it's off by more than beta is e to the minus beta squared times c, only valid for beta small enough, only valid for beta smaller than root k. So this you have to refer back to the Gaussian annulus theorem we proved. So that's not valid. We didn't prove it for epsilon greater than 1. But luckily, we only need it for epsilon less than 1. So all results about these concentration results, the large deviations are always difficult. So if you want a deviation greater than a certain amount, it doesn't behave like a Gaussian quite often. but these kinds of deviations behaves like Gaussian, which means I have a beta squared in the exponent, right? Beta squared. After a while, large deviations behave with e to the minus beta. We saw that for coin tosses last time, right? So we get this. So the probability is e to the minus k epsilon squared. So beta is k epsilon. So that's the first theorem. Okay. We do have to use the Gaussian annulus theorem to prove that, which we proved already. Okay. Theorem 2 is, as I said, union bound. So we have n squared pairs of points. Probability of failure for each is e to the minus c k epsilon squared. So with this k, if I put a log n there over epsilon squared, e to the minus c log n, I can make that 1 over n cubed or 1 over n squared. Okay, so it's important, as we said, exponential in k, so that k only grows logarithmically. Okay. So now I want to show you a couple of slides of applications. So here, so be prepared to answer some questions. Let's see how that goes. So k means clustering. Here's the problem. I'll draw a picture on the board. Given n points in Rd, you have to partition into k parts so as to minimize the sum of squared distances to the cluster center of each part. So if I had, I should have shown you some pictures, I guess. Yeah. So now I want to partition them into 5 parts, let's say. So I drew it so that there's a natural set of 5 parts. Okay, these are the 5 clusters. I partitioned the set of points into 5 sets. After I do that, I put down, maybe one more point will be nice to see. So I put down some cluster center for each cluster. I'm allowed to choose any cluster center, and then I take the distances, square them, and add. And I want to minimize that. It's not difficult to see that the best choice of center, once I give you the clustering, is just the mean of the cluster, right? That's only true for distance squared. So even on the line, you can convince yourself, I give you a bunch of points. I want a point mu, so that sum over x minus mu squared is minimum. And that happens exactly at one point when mu is the average of all the x's. It's only true if it means distance squared. Actually, there's going to be other properties that are only true for distance squared, which are not true for other metrics. We'll see that. So that's true. Okay. So here is a question. So this we are going to spend a few minutes thinking about. It's an important question. So is the following obvious? So I want to divide this up into k parts, right? I know that if I project to some number of dimensions randomly, as we just saw in the theorem, okay, all distances are preserved to 1 plus or minus epsilon. Okay. Therefore, why don't I just project and then cluster in the projection? After all the distances are preserved, so that should give me a near optimal answer within 1 plus or minus epsilon. So is this true? Is this a proof? Let's think about this. So can I use the theorem to argue that since the distances are preserved, I might as well project down and cluster? Okay. So the thing to think about is how I prove theorem 2 from theorem 1. Sorry? The epsilons might add up. So something like that, but add up, what epsilons would add up? It's a fair thing that something adds up, yes. So actually, the reason I put the question is this is false. False. Okay, I can't disprove it, but this is not a proof. and you cannot carry out a proof on these lines. It is true the distances are preserved. We proved that. Okay, it's a tricky question, so let's see that. So how many distances need to be preserved? This is the important thing. For theorem 2, we only had n squared distances to be preserved. Crudely, how many possible cluster centers could there be? Well, every subset could be a potential cluster. And there are 2 to the n subsets. Each of them gives you a point which is a mean, and each such point is a possible cluster center, right? Cannot rule it out. We cannot rule out which clusters will be formed. Okay? Therefore, if I want this argument to be made rigorous, I've got to take distances from each possible cluster center to each data point. There are 2 to the n cluster centers. So there are 2 to the n events, and I have to add up the failure probabilities. That's very bad. Okay. Then you'll see that k has to be very large. Everybody see at least the argument why the proof is fallacious, right? So this proof is not true. Okay. This is false. But for k-means, there's an easy fix, which doesn't apply to other criteria. Okay. Luckily, for any m points, one can prove that the sum of squared distances to the mean, S is a set of points, sorry, is the average sum of pairwise distances among all of S. So let me just draw that. I should prove that. I should have proved that on the slide. I'm going to write down a proof on the board. I didn't have time to. So we have a set S of points, and this is asserting there are n points. This is asserting that sum of x belonging to S, x minus x bar squared is 1 over S times sum over all xy belonging to S. This is only true for squares. See, I always may get this wrong. It might be S minus 1. So this is not a very difficult proof. Maybe if I run out of things to say at the end of the lecture, we'll prove that. You can try to prove this. It's very simple. Okay. Okay. So this is only true if it's square. If I didn't have a square there, it's not true. Okay, in general. So only with a square. So there are a lot of nice things that happen with a square, and this is one of the nice things. Actually, there are 2 nice things that happen with a square. On this slide, this is only true for square, and this is only true for square. Okay. So now can I make this assertion? Now can I make a projection? And what has changed after I told you this? How many distances does the projection have to preserve now after I told you this? So before I told you this, I was worried that 2 to the n distances have to be preserved, right? Yeah, it's only n squared because it's enough to preserve distances between all pairs of points. Once I tell you the distance between every pair of points, then the value of every clustering is fixed. That's what this is saying, right? And therefore, if I preserve those distances, I'm in good shape. Okay, so for k-means, projections do work. So you should think about, okay, I said that already. You should think about another criteria, many criteria that are used. Another criterion is k-median, where you want to minimize the sum of distances with no square, sum of distances to cluster centers. Then this argument is not correct. It does not work, right? So there is a way to project to get within a factor of 2 for k-median. But 1 plus epsilon, no. Okay. K means we lucked out. Okay, so this is now going to a different topic, Gaussian mixtures, which is in that chapter, but we'll prove this perhaps later. It's also a clustering problem. We won't actually have special lectures just on clustering, but this Gaussian mixtures I want to do, which has to do with clustering. We'll see that twice. Today we'll see Gaussian mixtures, and then when we do SVD, we'll see a better algorithm. Okay. Now, any questions on random projections before we go on to Gaussian mixtures? No, because it's got to be exact, right? Because we want to argue the optimal solution here is a near optimal solution up on top. If we get an upper bound, that's going to say that the cost in the projection is at most the cost in there, right? But it might be spuriously much smaller for something that's very costly here. And that might be optimal here, and I get the wrong answer. That's actually a good question. So I think we should go over this argument that, so if every distance is preserved, then the optimal answer is the same, right? But the argument for that has to go both ways. First, I have to say, if I get an optimal thing here, that's less than or equal to everybody else, therefore, also on top, it's less than or equal to. So an optimal here is very good there, but also I have to argue an optimal there is very good here. Okay. So as a good exercise, if I tell you all distances are exactly preserved, I have two problems with n points each. The distances are exactly the same. I get the same optimal solution. I mean, that seems trivial, but when they are approximate, you have some work to do. Okay, good point. I should have done that. Okay, so random projections do not preserve angles. They preserve lengths, they do not preserve angles. That's a good point to make. Okay, good. So if I have two vectors u and v, I have a random p, random projection p, then it's not true that the angle between pu and pv is not equal to, in any scaled way, the angle between u and v, right? So angles are not preserved. By random projections. Neither are dot products. Preserved means to relative error. Okay, so let's see why dot products are not preserved. That probably is not that difficult, right? So what can happen to dot products? So dot products need not be preserved by projections. So you can get the wrong answer when you project. Distances are preserved. Okay. So let's say that I have two vectors u and v. I want to worry about the dot product. I can write the following. This is the usual trick to express dot products in terms of length. Okay. So if I project pu squared is 1 plus or minus epsilon u squared, let's say. So then if I plug that in here, I will get p of u minus v squared length is 1 plus or minus epsilon u minus v squared. Okay. On the right-hand side, the errors add up. So the right-hand side, the errors become epsilon times u squared plus v squared. If now my dot product is very small, if they're orthogonal, for instance, u and v, the dot product is 0. In the projection, they won't be exactly orthogonal, nearly orthogonal. And so you don't preserve relative error, right? So that's the same as saying here that if the error is so much, it swamps the error in the dot product. So dot products are not preserved, and therefore angles are not preserved. Okay? because angles are just the dot product divided by the product of the lengths. The denominator is preserved, the numerator is not, so they won't be preserved. Okay. So dot products are difficult to do with random projections. Whenever some problem involves only distances you can do, but not otherwise. Okay, that probably is a good idea to put into the lecture, right? So. Okay, on to Gaussian mixtures then, right? So a Gaussian mixture is a probability density. Sorry, yeah.
One more clarification. So you saw something about sum to the square, right? That was you can handle.
Yeah.
But moment to the median, I don't have the square.
That's right.
But I still have the distances.
Yeah.
And so still adding distances.
Still adding distances. That's still true, but the number of distances that need to be preserved seem to be exponential.
So I can't get that 1 by m.
Actually, there are some other constructions called core sets, which are more complicated, by which you can do something. But I wasn't going to get into that. But you can't do. It's not true that pairwise. So the following is not necessarily true. If I told you there are two problems, two sets of endpoints, all pairwise distances are the same, is it true that the k median clustering will be the same? I think the answer is no. I don't know an example. I mean, you can try to construct an example. So it's not purely a function just of pairwise distances.
I believe the classical problem was Fermat's problem.
The median problem, yeah. Yeah, anything except squares is. You can give it in a factor of 2. That's not difficult. But okay. Okay, Gaussian mixtures. It's just a convex combination of probability densities, which are Gaussians. Again, a picture. So this is one Gaussian density. There might be another one, right? So I can take half of this density plus half of this. What that just means is that just add the weighted combination of the densities, right? So weights are WT. There are K densities. The WTs are non-negative, adding up to 1. It's a convex combination. That's just the exponential density with. I'm talking about now standard spherical Gaussians now, variance 1. Mu t are the means, right? So just like this picture, the mu t's are this and that. Add them up. The problem to do with Gaussian mixtures is samples from a mixture are given to you. So the real problem is the reverse problem. It's not the problem of taking the mixture and then generating points, but it's the problem of fitting a mixture to data that's given. So we are given data, which is x1 through xn. Their IID draws from that probability density. And ideally, from here you have to just find p of x. And here's another way to say that. An equivalent thing I can do to pick the samples. So I want to pick n samples. For each sample I pick a t, a component of the mixture, one particular Gaussian. And then I pick those components with probabilities proportional to the weights, right? W1 to Wk. And then pick xi from that density, right? You should convince yourself that these two are the same. The distribution of x1 through xn will be the same. Or the distribution of x1 will be the same as IIDF4. Okay. And the learning problem we want to solve, or the model fitting problem, if you will, I give you samples xi. I don't tell you which Gaussian it was drawn from. I, of course, don't tell you the mu t's. I don't tell you the means, right? We want to find the t for each I. That's a clustering problem. Once I find that, I can fit a single Gaussian to each cluster. So I erase that. So in this picture, you'll get samples like this. This is real, right? Okay. So I'll get only the points on the real line, in general in d-dimensional space. And I tell you two clusters, so the right clustering would be this and this. Okay, I've not drawn them very well, but this and this, right? Then I take all these points and I have to fit a single Gaussian to them. In the book, actually, we worked that out. You should know how to do that. So if you have a collection of things drawn from one Gaussian, fitting the Gaussian is easy. You just take the sample mean to be the mean of your Gaussian and the sample variance, or the sample variance covariance matrix in general to be that of the Gaussian. That's the best fit. Okay. So you can do that, but the problem of identifying the clusters is not trivial, is the real problem to solve. And the solution I want to say the following. Let's pretend the number of clusters is constant. I like to solve the learning problem if means of each pair of Gaussians are separated by 10 standard deviations. So this is a mnemonic that you hear all the time, right? Means separated by 6 standard deviations, let's say 10, or any constant. I want to say that's enough for me to learn the Gaussians. Okay? This is not trivial. In one dimension it is, but in d dimensions it is not trivial. So we like to prove, of course. We like to come up with a learning algorithm and prove that that works under this condition. Another way to say that is k may not be constant. The number of standard deviations, the means should be apart, can be something depending on k. So in these two, in this case, right, whatever, the standard deviation is about this much, and you better be separated by a constant times that. If the Gaussians are less separated, if they move on each other, there's no way to figure out the individual ones, right? So you can, in one dimension it's easy to see that you need that many and that you can do. So we will see that, in this lecture, we will see that distance-based clustering can do this only if the separation is d to the 1/4 standard deviation. So the number of standard deviations, the means have to be apart, has to grow with d for us to do it based purely on distances. Purely on distances means I take 2 points, and if they are close, I put them in one cluster. If they are far, I put them in different clusters. Let's say there are 2 clusters, right? That's all I'm allowed to do. Then you need a much bigger separation than the best. In next chapter, SVD-based algorithms will be able to do with the best possible separation, namely a number of standard deviations which is constant. We'll see that when we do SVD. Sorry, there was a question. Well, okay, so I will actually say that in the bend. If you want to get everybody right, you need an extra root log n factor. So this is getting most things right. In the end, I'll say that. If you want to get every point right, you have to pay an extra root log n factor. Okay. This is only going to get most things right. So everybody see the problem? So mean separated by a few standard deviations. Now, why is that difficult? So that actually in d dimensions, this is one picture I saw from the book, so I didn't actually sit and draw it. So I guess it doesn't quite illustrate things as well. I'll draw a better picture on the board. Maybe that's better. So we are sitting in d dimensions, d large, okay, and we have standard Gaussian. So we have e to the minus x squared over 2. So standard deviation is 1 in each direction. How does the Gaussian look like? We already saw that, right? We saw that the expected distance squared of the point is about d. Not about, it's exactly d. Okay, we saw this already, right? Therefore, things will be at distance about root d from the center. So most of the probability mass is here. Okay. Let's say I have 2 Gaussians with means separated by a few standard deviations. Standard deviation is 1, right? So, and this is root d. Think of d as very large, as root d as much, much bigger than 1. So the next Gaussian is centered here, and it looks like this. And this picture should tell you the problem, right? I've given you 2 Gaussians with masses concentrated in the 2 annulus, and I have to tell them apart. That's pretty difficult. They are not geometrically completely separated. Okay. So you can call this the sun and planets picture, right? So the distance is enormous compared to the separations. Okay. That's a difficulty in d dimensions. So I guess I'm trying to draw that there, but I'm not sure I did a very good job there. So this is the picture that I want to focus on. I want to separate the annulus. Now, of course, if I draw a hyperplane here, it is true, although the picture doesn't look nice like that, it is, even if this was 100, it is true that most points of this Gaussian are on this side, most points of that Gaussian are on that side. Okay, you have to prove that, but that's true. The picture doesn't look like that at all, but it's true, right? And if I give you 100 root log, and every point is like that. Okay. Now what's the difficulty with this? The difficulty with this, I don't know this hyperplane. Okay. Right? Now, if only I could project to the space of, if only I knew the centers, and I was able to project orthogonal to that. So in this case, so one-dimensional subspace, I project orthogonal, then the Gaussians, well separated, they look like this in the projection. Again, something you have to prove. Okay? So I have to find this projection to be able to do this. Then I will be home. It turns out SVD, this is an SVD subspace. SVD does that. This is a preview. We won't see that till a few lectures. We will see that actually, a proof of that when we do SVD. Right now, we are focusing on figuring out if based just on distances I can do something. And the answer is no in this case. I cannot do it. So two spherical Gaussians with unit variance in every direction. If x and y are independent samples from the first Gaussian, then, okay, maybe I should draw the picture again. So x is one sample for the first Gaussian. It's always in that annulus. And y is another sample. Oh, that was that picture, actually. That is the first picture, right? So the picture looks like that. And they're almost or nearly orthogonal. We saw that. We've seen a proof of that. And in this picture, that indicates that this is the distance between them. Because they are almost orthogonal, each a distance root t from the origin, the distance is square root of 2 times square root of t. If I now have, so first maybe I'll explain the picture and then we'll do the calculation. Now that I have two Gaussians separated by delta. I've drawn delta to be very large just to do the calculation. The first point, x is picked from the first Gaussian. Point y is picked from the second Gaussian. Let's see the distance between them. That distance, the vector is, I go from x to its center, and I go from the center P to Q, and I go from Q to this. Now, let's pretend that this is 90 degrees, this angle. Also, this is 90 degrees. It doesn't look like 90 degrees, but it is 90 degrees, right? So why is it almost 90 degrees? So I want to claim that angle XPQ and angle PQY are both about 90 degrees. What theorem that we proved may tell us that? We proved a theorem to that effect, right? And that theorem is sort of, the theorem we proved is sort of this picture. And this picture says this vector and this vector are almost orthogonal. And that's because what? This vector so what is the name of that theorem? So that was the equator theorem, right? So this vector, they're independent, so I might as well have picked this vector first. Then when I'm picking this vector, that's a fixed direction. We made it the North Pole. We know that this vector lies close to the equator, which means more or less orthogonal. We saw that the angle is 1 over root t. Is cosine inverse of 1 over root, or sine inverse of 1 over root t. No, cosine inverse of 1 over root t, that angle, right? So this line, P to Q, the centers were fixed before we picked any points. They're not random. So this is a fixed thing, therefore this is orthogonal to it nearly. Okay, and once I fix this and that, this is orthogonal nearly to both of them. This is two equators. So x defines an equator of this sphere, and PQ defines another equator. You didn't draw all that, and QY is orthogonal to both of them. So it's a sum of squares. So you get D for the square here, D for the square there, 2D, and delta squared. Okay. So I worked this out on the next slide. That's the same. That was a picture proof. This was a real proof. If x and y are two linearly independent, or sorry, not linearly, stochastically independent samples from the first Gaussian, then I want to figure out what x minus y squared is. I expand it, right? I get x squared y squared minus 2x dot y. X squared is d plus or minus, this is the Gaussian annulus theorem. Okay. Y squared, also Gaussian annulus theorem. Plus or minus order root d means it's at most absolute value order root d. Okay, as add or subtract. 2xy is order root d. Now, why is that? So x and y are independent samples from the same Gaussian 0, 1. So I want to know what x dot y looks like. What's the distribution of x dot y? Okay. I fix x, right? And then y is random. So this is xj, yj. This is the sum of, and so x is fixed, y is random normal 0, 1, right? And again, independent, so on and so forth. You add up the variances, you get sum of 0, x squared. X squared is about d, sum of 0, d. Again, it requires a little bit of proof to show all this. So x dot y is normal 0, d. D is this variance, so it's about order root d. Again, you have to pin down more rigorously these calculations, but that is true. If the two centers are delta apart and x and z, or respectively from the two different Gaussians, then I get, this was the second picture in the last slide. This I expand, there are three terms here. Okay. Again, the cross terms are very small, and they run out of the slide anyway because they're very small. But the most of the main terms are just sum of squares. They're orthogonal. So this square plus this square. So you get this and this, or d each. So I get 2d. I think that also ran out of the slide. Okay. Yeah, it ran out of the slide. So same is 2d plus or minus order root d. Different is 2d plus delta squared plus or minus order root d. Okay. So distance-based clustering works if 2 points from the same Gaussian or closer to each other than 2 points from different Gaussians, and that requires this be always greater than that. The worst case of this is delta squared minus c root d, and that must be greater than the best case of this. Sorry, there's a 2d here. 2d plus root d. So then you need delta squared greater than root d, or delta greater than d to the 1/4. So once the separation goes below d to the 1/4, you cannot tell distance-wise. In fact, these calculations can be reversed. The converse is also true. Okay. Now, this is for one. We didn't do the calculations quite right. There was, as the question was right, what do we do with all points? So if you put an extra root log n factor, because it's Gaussians in e to the minus x squared, with the minus root log n, sorry, extra root log n factor, you get failure probability for each distance goes down as 1 over n cubed or something. So it works for all of them. So what is this? The moral of the story is you need a very large separation between the means, more than standard deviation number of separations before you can tell the Gaussians apart, even two of them spherical. this can be generalized to any number and can be generalized. A lot of work has been done. I mean, this is sort of an active research area. A lot of work has been done and being done on learning Gaussian mixtures. So it looks like that was the last slide. So even though we're supposed to go to the 5, I could finish unless there are questions. So we could have some discussion or questions if you. Oh, otherwise we meet on Thursday next, right? Number 1. Number 2, this is going faster than I expected, right? So on Thursday, I'll already start the SVD chapter. And because it's going faster, we will hopefully do, at the end, massive data matrix computations using sampling. That's in a later chapter, I think chapter 7 or 8. So, massive data matrix algorithms. And in that we will do also SVD and all that, but we'll do it with sampling. So the order of business is 1, Thursday will be start of SVD. It'll probably run for 3 lectures and then we'll branch off into other things. Sorry. Yeah, sorry, yes, it's one of the terms there. There is a, I think that's right, it's delta root D, right? Delta. No, I'm sorry, it's not delta root D. No, it's only delta. So this has length delta. This has length D, length root D, sorry, right? The dot product is 1 root D off. 2 random vectors, the dot product is root D factor less than being collinear. So if they had been collinear, it would have been delta root D divided by root D is a delta. The so delta squared should be greater than delta as well as root D. And del is greater than delta is a trivial inequality, so it's greater than root D. I'm sorry, so I guess I will write this down more carefully and put it in the slides. But yeah, so yeah, I think you need only delta greater than D to the 1/4, provided D is large enough. Yeah, once you have the right projection, you can do it. So maybe you're saying information theoretically, what? Yeah. If you're not worried about an efficient algorithm, then mean separated by a fixed number of constant standard deviations is enough. So if you're worried about a polynomial term algorithm, though, then it's not. Then it's enough still with SVD, but not without SVD. Yeah, so I guess that's a good distinction. So information theoretically, it's enough that the number of separation is a few standard deviations, large constant standard deviations. The first thing is that if instead of separation based on standard deviations are different in different directions. So I take the maximum of all standard deviations, of all Gaussians. If I have that much separation, I can do it. Okay, that is somewhat, that's 20 years old, maybe, in the 90s actually. So, so I think, yeah, there was a paper of Sanjeev Arora's and mine, which we proved things like that. But then people worried about more what's called the pancake problem, which is very nice. So you have 2 Gaussians, which are very long and skinny, like that. So their standard deviations in this direction is small, but in every other direction is huge. And they are separated by 100 standard deviations in that direction. But by no means, this is by no means 100 times the maximum standard deviation. Can you tell them? It turns out to be a hard problem. You can now, we know how to do it now for 2 Gaussians. I'm not sure we still know how to do it for k Gaussians for the pancake problem. Okay. So what standard is, okay, what is standard is separation between means, which is omega of maximum standard deviation. This is old, right? Then that's okay. But ideally, you would like the standard deviation, the direction joining the centers, and I give you 100 times that separation. Can you do it? That's not easy. So it's probably, for instance, not true that if I do SVD, I get this direction. If I do, again, this is looking up because we haven't done SVD yet, but if we did SVD, then we won't get this direction, right? It's actually the least singular value direction rather than the most. The techniques are different, yeah. So in fact, what you do here is throw away the least singular values and work your way up. So something different. It's somewhat PCA related, somewhat related to singular values, singular vectors, but not quite directly. The eigenstructure is still used. Okay, so if you want to know more about any of these things, you can ask me for references. And both random projections, Gaussian mixtures, and so on are topics of current interest in research. So.